Imagine your site gets a billion visitors and someone asks a simple question: how many of them were actually different people? Not the total clicks. The unique ones? You'd think you'd need to remember every single visitor to answer that, and that would cost you gigabytes of memory. But there's a structure that answers it using less memory than a text message. A billion unique things, counted, in about the space of a short paragraph. It sounds impossible. By the end of this video, you'll understand exactly how it works, and it's one of the most beautiful ideas in computer science. The structure is called HyperLogLog, and it has a strange and wonderful property. The amount of memory it uses does not grow with the count. Whether you're counting 100 unique visitors or 100 million, it sips the same tiny fixed amount of space. Redis, the database, uses a version that fits in 12 kilobytes and answers within about 1% of the true number. Let's start with why this is hard in the first place, because the obvious approach falls apart fast. Say you want to count distinct visitors the honest way. Every time someone arrives, you check, have I seen this person before? To answer that, you have to keep a list or a set of everyone you've already seen. One unique visitor, one entry. The problem is obvious once you say it out loud. To count a billion different people, you have to store a billion identities. The memory grows in lockstep with the count. Counting more costs more, forever. That's the wall we need to get around. So here's the goal, stated plainly. We want to count the number of distinct things in a massive stream, using an amount of memory that stays small and fixed no matter how high the count climbs. We are willing to give up something to get there, perfect accuracy. The answer won't be exact. It'll be an estimate, off by maybe 1%. And for counting unique visitors, that trade is almost always worth it. Now, how on earth do you estimate a count without remembering what you've seen? The whole trick rests on one idea, and it's the heart of the algorithm, so let's take it slowly. The first move is hashing. You run every item through a hash function, which scrambles it into a string of bits that looks completely random. Each bit is a 0 or a 1, like a coin flip. And here's the crucial part. The same item always hashes to the same bits. So if a visitor comes back, they produce the very same pattern, and they don't change anything. Duplicates are free. Now stare at one of those hashes as a row of bits. Because every bit is like a coin flip, ask a specific question: how many zeros appear at the very start before you hit the first one? Most of the time, the answer is small. The first bit is 1 about half the time, so half of all hashes have 0 leading zeros. A hash starting with a single 0, then a 1, happens a quarter of the time. 2 leading zeros, an eighth. The more leading zeros you demand, the rarer it gets. Let that sink in, because it's the key. A run of leading zeros is a rare event, and the longer the run, the rarer it is. Seeing 5 zeros in a row at the start of a hash is like flipping a coin and getting 5 heads in a row. It only happens about 1 time in 32. 10 leading zeros is like 10 heads in a row, roughly 1 in 1,000. The length of that leading run is a tiny built-in rarity meter baked right into the bits. And here is the leap that makes the whole thing work. Suppose a friend tells you the longest streak of heads they ever flipped was 10 in a row. You didn't watch. You don't know how many times they flipped. But you can make a shrewd bet they probably flipped that coin around 1,000 times. Because a streak of 10 heads only tends to show up after about 1,000 tries. The rarest thing that happened quietly reveals the scale of how much happened. They never counted, and yet the count is hiding in the streak. That bet is the entire algorithm. Run every item through the hash, and just remember one number, the longest run of leading zeros you have ever seen across all of them. Call that longest run the max. Then your estimate for how many distinct items you've counted is simply 2 raised to that max. Saw a run of 10 zeros at most? You've probably seen around 1,000 distinct things. Saw 20? Around 1,000,000. You remembered a single small number, and from it you recovered a count. No list. No set. One number. Pause on what just happened, because it's genuinely strange. We threw away every item. We never stored a single identity. All we kept was the length of the most extreme zero run we stumbled across, and that one length lets us guess the size of the whole crowd. And duplicates change nothing, because a repeated item hashes to the same bits and the same run we've already accounted for. This is the seed of HyperLogLog. Everything from here on is about making this estimate trustworthy, because right now it is not. Here's the problem with our one-number estimate: it's wildly noisy. It depends entirely on the single luckiest hash we happen to see. Get one freakishly long run of zeros by pure chance early on, and your estimate doubles or quadruples instantly. And because the estimate is always 2 raised to some whole number, it can only ever land on a power of 2, 1,000, or 2,000, or 4,000 with nothing in between. One unlucky hash and you're wildly wrong. We need to calm this down. The fix is when you already know if you've ever run an experiment, don't trust a single trial, run many, and combine them. So instead of keeping one max run for everything, we split our items into many separate groups called registers or buckets. We do it using the hash itself. Take the first few bits of each hash to choose which bucket that item belongs to, and use the rest of the bits to count its leading zeros. Each bucket then quietly tracks its own longest run, completely independently. And the elegant part is that this is still just one hash per item, sliced in two. The front slice picks a bucket, the back slice feeds the leading zero count for that bucket. An item always lands in the same bucket because it always hashes the same way. So now, instead of one noisy experiment, you're running thousands of them in parallel, each one watching a random slice of the stream and remembering its own longest streak. Many independent guesses, all at once, from a single pass over the data. Now you have thousands of buckets, each holding its own max run, each a small and noisy estimate of the whole. The instinct is to average them. And we do combine them, but not with a plain average. A plain average is too easily wrecked by one unlucky bucket with a freakishly long run, which drags the whole thing up. Instead, HyperLogLog uses a harmonic mean, a kind of averaging that pulls hard toward the smaller, more typical values and refuses to let one extreme outlier run away with the answer. That harmonic mean is exactly where the name comes from. An earlier algorithm called LogLog combined its buckets a cruder way and got a shakier answer. Swapping in the harmonic mean tamed the noise so well that the authors called the upgrade HyperLogLog. It crushes the variance, turning thousands of jittery power of 2 guesses into one smooth, stable number. The more buckets you use, the steadier that number gets. Accuracy is bought with buckets, not with memory per item, and that distinction is everything. There's one last touch of polish. The raw combined number comes out slightly biased, consistently a little off in a predictable direction, so the algorithm multiplies it by a correction constant that nudges it back onto the truth. And at the very extremes, when you've counted almost nothing, or a staggering amount, HyperLogLog quietly switches to a different formula better suited to those edges. Small details, but they're what take it from a clever idea to a production-grade tool you can actually rely on. Let's put the real machine on screen. Redis uses 16,000 buckets. Each bucket needs just 6 bits to store its longest run because the run can never get very long. Multiply it out, and the whole structure fits in 12 kilobytes. That is the entire memory cost. 12 kilobytes to count unique items, whether there are 1,000 of them or 1 billion. The crowd can grow without limit, and the meter measuring it never gets any heavier. And how wrong is it in exchange for that? With 16,000 buckets, the typical error is about 0.8%. Under 1%. Count 10 million unique visitors, and HyperLogLog will usually land within a whisker of the truth, while spending less memory than the text of this sentence. There's a famous figure from the original paper of 1 billion items counted in around 1.5 kilobytes, using fewer buckets and accepting a slightly larger error of a couple of percent. Same idea, dialed for size over precision. It's worth pausing on what that error number really means. The accuracy depends only on how many buckets you choose, and not at all on how many items you count. Read that again. A bigger crowd does not make the answer worse. The 1% holds whether you're counting 100 things or 100 million. In a world where almost everything gets harder at scale, HyperLogLog's accuracy simply does not care how big your stream gets. That is a rare and precious property. How high can it count? Redis hashes into 64 bits, which means it can estimate counts all the way up to 2 to the 64. That's about 18 quintillion, a number with 19 digits, far more distinct things than exist on the entire internet. You will run out of unique items in the universe long before you run out of HyperLogLog. And the whole time, it never grows past those same 12 kilobytes. Fixed memory, astronomical range. In Redis, this lives behind 2 friendly commands. You call PFADD to throw an item into the sketch, and PFCOUNT to ask how many distinct items it has seen. Here we add Alice, then Bob, then Alice again, and ask for the count. It returns 2, not 3, because the second Alice hashed to the same bits she did the first time and changed nothing. The PF, by the way, honors Philippe Flageolet, the researcher who invented the technique. You're using his coin flip insight every time you call it. One thing HyperLogLog cannot do, and it's important to be honest about it, it stores no items at all, only those small bucket counters. So you can never ask it, did Alice visit? It has no idea. It threw her away the moment it hashed her. It only ever answers one question, how many distinct, and never which ones. If you need to ask whether a specific thing is present, that's a different tool, a Bloom filter. HyperLogLog counts the crowd. It does not know any of their names. There's one more superpower that makes it beloved at scale. 2 HyperLogLog sketches can be merged into one that counts all their unique items combined, just by taking the larger run in each matching bucket. So you keep a small daily sketch of unique visitors, and at the end of the month you merge 30 of them into a single monthly unique count, without ever rereading the raw logs. But beware the classic trap. You cannot simply add 2 counts together, because that would double count anyone who showed up on both days. You merge the sketches, then count once. This is exactly why HyperLogLog is quietly everywhere. Redis ships it. Google's BigQuery, Snowflake, and Presto all use it to answer count distinct queries that would otherwise crawl, turning jobs that once took days into ones that finish in hours. Druid, ClickHouse, and Elasticsearch lean on it too. Anytime a dashboard tells you unique users, unique searches, or unique devices over a huge time window, there's a very good chance a HyperLogLog is doing the counting underneath. Let's retrace the whole idea, because it's worth holding all at once. Hash each item so its bits look like coin flips. A long run of leading zeros is rare, so the longest run you ever see hints at how many distinct items passed by, roughly 2 raised to that run. One estimate is too noisy, so you split into thousands of buckets, each tracking its own longest run. You combine them with a harmonic mean to crush the noise, then correct the bias. That's it. That's HyperLogLog. And what you get from those 5 steps still feels like a magic trick. A structure that counts up to billions of unique things in 12 kilobytes within about 1%, while storing not a single one of the items it counts. It works in one pass, in any order, and the cost never grows with the count. The deepest lessons in computer science are often like this. You give up a sliver of perfection, and in return you get something that scales to the size of the entire world. So the next time you see a dashboard casually report a billion unique visitors, you'll know the quiet secret behind that number. Nobody kept a list of a billion people. Somewhere, a hash function turned each visitor into coin flips, and a few thousand little counters watched for the longest streak, and from the rarest thing that happened, the size of the whole crowd fell out. Less memory than a text message. That's the kind of idea that makes computer science click.